So, perceiving our world is essential for creating memories, acquiring knowledge, solving problems, and communicating ideas. Perception, visual perception, auditory perception, really perception in any form, perception based on any sensory system is quite difficult. It's a complicated problem for the brain to solve, in part because we're interpreting incomplete information. And so what we're going to look at in this lecture is why visual perception is difficult, why speech perception is difficult, and we'll talk a little bit about what our brains do to overcome problems that make perceptual experience challenging. Something to keep in mind throughout this lecture is the idea that perception is a creation of the mind. Perception does not directly reflect the sensory signals we receive, right? It's not entirely bottom-up. And we can see that in this dynamic Mueller-Lyer illusion on the right here. So the blue and the black lines are the exact same length. They never change. But the way this illusion works is because the angled lines are moving, they provide a context in which the blue lines seem to grow and shrink in size, even though they're actually not changing at all. And the point of this illusion is just to demonstrate that we can interpret the same sensory signals in multiple ways. So here's another example of a misinterpretation of sensory signals, right? You look at this picture, you think you have it figured out. It's somebody standing up leaning against a tree, and then you rotate your head. In this case, I've flipped the image 90 degrees, and you have a different understanding of what's happening based on similar sensory signals. So why is visual perception so challenging? Right? If you're a fan of Star Wars, you're used to seeing robots that have advanced robotic visual systems. And actually, scientists, PhDs, engineers have been working on this problem for a very, very long time, creating computers that can see. And they've been working on this problem because the self-driving car would arguably, dramatically improve our lives. Imagine if you didn't have to drive anymore. Imagine if you could get in a car and it could take you wherever you wanted to go, and you wouldn't have to think about driving. You wouldn't have to concentrate on driving. This would dramatically change our lives. Now, this will eventually happen. It might be, decades away, but this problem has been worked on by literally thousands of people with PhDs for about 60 years now. And so we can go all the way back to the 1960s and the invention of something called the Stanford cart. This was arguably the first self-driving vehicle with a computer vision system. And it took the Stanford cart 10 to 15 minutes to plan every 1 meter move, and the cart could only follow a white line painted on the road. Now, 60 years later, we have much more advanced self-driving cars with more advanced computer vision systems. One of those is the Google Waymo, which has been deployed in several American cities, and you can actually hire one as a taxi to take you around cities like Phoenix, Arizona. And I'm going to show you a video of the Google Waymo in action. And, it's really impressive technology, but again, I think it's important to think about just how many people have worked on this problem, for a very long time. And the self-driving cars that we have now, like the Google Waymo, like Tesla's, advanced sort of autonomous driving systems, are not as good as your 16 or 17-year-old driver who, just got their license. So I'm going to show you a video of the Google Waymo in action.
Waymo has been operating its self-driving cars in Arizona for about 1.5 years, and during that time, it's even run them without safety drivers behind the wheel. Waymo's cars collect a ton of data, and Waymo feeds that into its deep learning algorithm for labeling and processing, and this allows Waymo to deploy what it calls the safest driver on the road. Now Waymo is ready to start taking on passengers and create a real business for itself. It works basically the same way as any ride-sharing service. You pull out the app, you pick your destination, and hail a ride. A few minutes later, one of Waymo's self-driving Chrysler Pacifica minivans pulls up. These are covered in high-powered sensors, like LiDAR, radar, and ultrasonic, along with a bunch of cameras, to provide a full 360-degree omnidirectional field of view. Waymo is calling its taxi service Waymo One. And initially, we were going to show you a demo of the ride that we took through Chandler, but truthfully, it was kind of long and kind of boring. Well, not entirely boring. There were these touchscreens behind the headrest that present a live view of what the car's sensors can see. Other vehicles are blue, pedestrians are white, and your trip is shown as a green line that the Waymo follows. It was pretty cool, but overall, the ride itself was uneventful, as it should be. It was like being in the back seat with a very cautious student driver. And sometimes it would take longer than usual to make a decision, like this unprotected left into a parking lot. Now this is going to be a complicated turn right here. We're taking a left-hand turn across traffic into this parking lot. So the car is sort of figuring out where it can go, when it can go. If there's no traffic signal or signage to tell us when to go, the car needs to make that determination itself. It needs to find that gap in the traffic. Waymo programs its cars to be conservative, to be safe drivers. A human driver probably would have gone right then. That might be comforting to some people. Other people might find that a little bit annoying and would want to see the car being a little bit more assertive. And that's something that Waymo is working on and has been sort of trying to develop its software, tune its software in a way that the car drives more organically, more like a human. There were moments when the car acted more aggressively than I expected, but it was the type of behavior that you wouldn't notice if you were being driven by a human driver. There were jerky moments, sure, but it never felt unsafe, and I never felt carsick for that matter.
So yeah, you might watch that video and think, wow, that, it's a really impressive self-driving car, and it is. But again, I think it's important to think about how long this problem has been worked on, how many smart people have been working on this problem, and, we're at sort of the peak of human technology here in terms of computer vision systems. And this self-driving car is like, as good as a student driver, basically. Any one of us would drive a car more efficiently and more effectively than the Google Waymo. Similarly, if we look at speech recognition systems, we see that, scientists have been working on this problem for a very, very long time. If we go back to the 1960s, IBM invented a machine called the shoebox that could recognize 16 commands like plus and minus and the numbers 0 to 10. Today, of course, we have things like Amazon Alexa and Siri on the iPhone, and these are pretty good speech recognition systems, but they still make mistakes, as you might have experienced if you have one of these systems. I have an Amazon Alexa, and I find it's constantly misinterpreting my questions. If there's any noise in the room whatsoever, it can't really understand my commands. So again, a situation where we're really struggling to build a machine that does something that, in this case, any 6-year-old human can do with very, very little effort. So why? Why is perception such a challenging problem, both in the visual domain and in the domain of speech? Let's look at some of the problems, and we'll start with vision. So the first thing to consider when we're talking about visual perception is that the source of things that we see in our world is ambiguous. Right now, you might be looking around your room or wherever you are right now and thinking, what does that mean? Like I'm looking at my computer screen. It's there. It's in front of me. I know it's there. It's sitting on a desk. I can, see a lamp in the corner of my room. And that's fine, but you're making those perceptual decisions based on a retinal image, right? So all you have is the image of your computer that's cast onto your retina. And that image, it turns out, can be created in many different ways. And this is known as the inverse projection problem. Perception starts with a retinal image, and that image is necessarily ambiguous. We don't know what object in our world created that image, and there are sometimes multiple ways to create the same retinal image. In this figure here, we can see that we can arrange this piece of paper in such a way that it can be in different places in our world and still create the same retinal image. So how do we know where things actually are? How do we make that decision based on this 2D representation that we have on our retina? Second problem for visual perception: objects are often hidden, right? But we don't really perceive them as hidden. We perceive them as complete. So if we look at the Toronto skyline, beautiful city. I grew up just north of Toronto. We see the CN Tower, and we know that it's complete even though we can't see its base. If we look at this crowd of people here, we know that each person is a complete whole, is an individual, even though we can only see a portion of their bodies. So this is really a remarkable thing, and it's a challenging problem for computer vision systems to solve. Third problem for visual perception: objects are often blurry, right? There's noise both in our external world, and I say that just as my heating kicked in, so you might be hearing some noise in the audio right now. There's noise both in our external world and in the firing of neurons, but you can still recognize people when they're far away. You can still recognize people when it's foggy out or when there's low light. And this is sort of a dramatic example of how good we are at actually recognizing faces when there's a lot of noise in the visual system. So these are blurred faces. And so I challenge you right now to identify each of these 7 individuals starting on the left. And I'll just give you a couple seconds to do that. And so the first image on the left is of course Will Smith. And then we have Taylor Swift, Barack Obama, Hillary Clinton, Jackie Chan, Ben Affleck, and Oprah Winfrey. Pretty remarkable that we can do that given how blurred these images are. Fourth problem for visual perception: objects look different from different viewpoints. But that kind of doesn't matter. Our visual system kind of doesn't care. You can look at this chair here from different angles. You still perceive it as the same chair, right? You don't perceive it as a entirely different object. And this is known as viewpoint invariance. So we recognize objects even when they're viewed from different viewpoints. Another way to think about this is different retinal images somehow result in the same perceptual experience. Very difficult problem for computer vision systems to solve. Our brains do it sort of quite easily. Finally, we're really good at extracting high-level information from scenes. So another way to say that is that we're really good at understanding the context of visual scenes. So for instance, look at this picture here. A computer might look at this image and identify that there are planes, identify that there are people, and it might surmise, based on that information, that these are people at an airport waiting to board a flight. But of course, we look at this image and we know that that can't possibly be true. How do we know that? Well, first of all, the planes look a little weird. When was the last time you flew on a propeller plane? Probably, maybe never. I've flown on a few propeller planes. They're pretty rare. But I think that's the point. They're pretty rare. When was the last time you waited on the tarmac to board a plane? This happens sometimes at small airports, but again, pretty rare, and you wouldn't be allowed to sort of freely roam around. And so we look at this image and we immediately are able to understand that, this is probably some sort of air show. These people aren't waiting to actually board these planes. So we're really good at extracting context from visual scenes. Computer vision systems really struggle with this. Again, a computer might identify people, might identify planes, but would struggle to surmise that this is some sort of air show. So those are some challenges to visual perception, and we'll talk a little bit in a second about how our brains surmount these challenges. But I just want to focus a little bit on speech perception. So right now you're perceiving the sound of my voice, and that's actually a very challenging problem. Why is that challenging? So it's challenging because words actually aren't produced in isolation. They slur together. And so if you just look at the acoustics of speech, you'll see this continuous stream of audio. And so this is an acoustical signal in this figure here for the phrase, mice eat oats and does eat oats and little lambs eat ivy. And you can't really see the breaks between the words. Yet when you hear me read that phrase, you perceive breaks between words. And this is known as speech segmentation. So we perceive words in isolation, even though the acoustics of speech are never produced, in isolation. It's one long acoustical signal. And so somehow our brain figures out where words start and where words stop. It's really a remarkable thing. Very challenging problem for speech recognition systems like you would find in for instance, Amazon Alexa. And that's why sometimes if you speak too quickly, right, Alexa has trouble understanding what you're saying. And so you're forced to slow your speech down and produce every word in isolation. Very unnatural way to talk. Second problem that makes speech perception hard is that there's a lot of variability in speakers and speaking contexts. I just mentioned that my heating came on, and so there was some noise in the room that might have made it harder for you to understand me, but you were able to actually surmount that problem, and it probably wasn't too difficult to make out what I was saying. There's variability in speech acoustics between speakers. Speakers of different genders have different pitches to their voice, different accents. People who speak with a Scottish accent, very, very clear. You can recognize it as a Scottish accent, but you can still understand them. And there's lots of environmental sounds, right? There's noise in the room. Someone might cough while they're speaking. There's environmental noise. And despite all of this variability, if I say the word bed, or somebody with a Scottish accent says the word bed, or somebody of a different gender says the word bed, you still perceive it as bed. So lots of variability in the way that we produce speech, but in the end, we all still perceive the same thing. Very difficult problem for speech recognition systems to solve, known as the lack of invariance problem. All right, so we've talked about what makes perception difficult in both the visual domain and in the domain of speech perception. And again, we could look at any sensory system and talk about touch perception, smell, taste, music perception, but I picked these two because these are very important aspects of our cognition and psychology. How do we start to solve these problems? So one way is that we bring a lot of prior knowledge to the problem of perception, right? And here's an example in vision. So visual perception is shaped dramatically by knowledge of what objects should exist in different scenes. And so this illusion here is known as multiple personalities of a blob. And so in each of these images, we have the exact same blob, visually speaking, and it's outlined by the dashed ovals. So each of these dashed ovals are identical in every single way. So when you look at these dashed ovals, the same visual signals are striking your retina. But in each of these scenes, you perceive the ovals as something different. In the top left-hand corner there, you might perceive a plate and some sort of cup on a table. In the top right-hand corner, you might perceive a phone. In the bottom right-hand corner, you probably perceive feet. And in the bottom left-hand corner, you probably perceive a car, a person, some sort of awning. And so we're able to use prior knowledge to disambiguate what would otherwise be a very ambiguous visual signal in this case. So where does that prior knowledge come from? Well, it's important to distinguish here between bottom-up information and top-down information. You may remember these terms from intro psych. So bottom-up information refers to information from the senses. Information being transduced by your sensory receptors. Top-down information refers to prior knowledge. And so this prior knowledge basically comes from learning and memory. We draw on prior knowledge extensively to help us perceive ambiguous visual signals and ambiguous speech signals. I'm going to give you an example of that now. So I'm going to play you a stream of speech that is known as noise-vocoded speech. And so what that means is that a lot of the richness of the speech signal has been stripped out, and it's going to be very difficult for you to understand what you're hearing. You probably won't understand it at all. Then I'm going to give you some prior knowledge, and suddenly the stream of audio will be quite clear. So here we go. And again, try to understand the speech that you're hearing, but you might not be able to understand it. A lot of the richness, timbre, we might say, has been stripped out of the speech signal, and so it's very, very difficult to understand. This type of speech actually mimics what people with cochlear implants hear when they listen to speech. So here we go. Let's see if you can do this. So that was probably quite difficult. I'm leaving my headphones on here so I can hear what's happening. I'm going to give you some prior knowledge now. I'm going to play you the original audio with its full sort of richness, and you'll be able to understand it. It's very clear speech. So here we go.
The BBC would like to announce that the next scene is not considered suitable for family viewing. It contains scenes of violence involving people's heads and arms getting chopped off, their ears nailed to trees, and their toenails pulled out in slow motion.
Okay, so presumably everybody understood that. Very clear speech. That version, again, is the original of what you initially heard. Okay? So I've given you some prior knowledge, and now I'm going to play you that original version again, the first one you heard that you couldn't understand. Now what you're going to find is because I've given you this prior knowledge, it's actually going to be remarkably clear.
The BBC would like to announce that the next scene is not considered suitable for family viewing. It contains scenes of violence involving people's heads and arms getting chopped off, their ears nailed to trees, and their toenails pulled out in slow motion.
And a lot of students, when I present this in class, they say that third example, that's different audio from what you first played. And it's not. It's the exact same noise-vocoded speech. It's just I've given you a bit of prior knowledge, and you're able to rapidly apply this prior knowledge, drawing it from working memory in this case, to disambiguate that ambiguous speech signal that you initially heard. So that's an example of top-down processing. Here's another cool example. This is known as phoneme restoration. Again, speech perception is shaped by our knowledge of speech that we've heard in the past, but also by our knowledge of what speech sounds should be in words. Okay, so we know what speech sounds normally come after other speech sounds, right? You have a consonant and then you typically have a vowel, for instance. And so in this perceptual phenomenon known as phoneme restoration, one speech sound is removed, in this case the S sound from the word legislatures, and it's replaced by a cough. And you will actually hear the S sound in that cough, even though there is no S sound there. And that's because your brain expects an S to exist in the word, because it understands how legislatures should be produced. And so it restores the missing phoneme. So I'll play you this example. I'll just put my headphones back on here.
The state governors met with their respective legislatures convening in the capital city. The state governors met with their respective legislatures convening in the capital city.
So again, the idea there is that that S sound is actually being completely removed, but you don't hear it like that. What you hear is the S sound sort of overlaid by the cough. And so what your brain is doing is it's actually taking the acoustics of the cough and filling in that missing S sound, because it knows how that word legislatures should sound. So again, this is an example of the application of top-down knowledge to perceive an ambiguous speech sound. Now I'll play you the version with the cough removed, and you will clearly hear that the S sound is being removed from the word. So here we go.
The state governors met with their respective legislatures convening in the capital city. The state governors met with their respective legislatures convening in the capital city.
This is an example where you really need that audio input for your brain to restore the missing phoneme. And the real world example of this is, when you're at that noisy party and talking to a friend and somebody laughs or coughs, your brain hears noisy speech and is able to sort of fill in the blanks, fill in the missing information based on prior knowledge. Really cool effect. So let's look at the role of top-down processing in visual perception, and this is just an example that I've taken from your textbook. There are many, many examples, including the multiple personalities of a blob that I showed you. So in this study, participants viewed a scene, and then we're asked to identify a very briefly presented object. So you view a scene, an object is flashed at you, 40 milliseconds, barely perceptible. So a very quick flash. And these objects were either appropriate to the scene, inappropriate to the scene, or they were sort of disguised. So they were looked like objects that could be scene appropriate, but they actually weren't scene appropriate. So here's an example of a scene that you might be shown. So kitchen countertop, you've got your cutting board, your butter, a knife, a toaster, and so on. And you'll view the scene, and then you'll have one of these objects flashed at you. So loaf of bread, this would be what we would call a scene appropriate object. A mailbox, so this kind of looks like the loaf of bread, right? So this is one of those situations where it's an object that looks like something that should be appropriate to the scene, but it's not. And then a drum, clearly not appropriate for this particular scene. And so what do they find? They found that prior knowledge drawn from the image that you were shown helped people identify these briefly presented objects, right? So if you're shown this kitchen countertop and then you're flashed a loaf of bread or a toaster for just 40 milliseconds, so the briefest of flashes, because you've been given this prior knowledge, because you've sort of been primed to think about, what's in a kitchen, you're actually a bit better at identifying these briefly presented objects than objects that are inappropriate to the scene, and much better at identifying appropriate objects and objects that look like they might be appropriate but actually aren't scene appropriate. So what we're seeing here is a bit of interference. So it's actually a bit harder to identify the mailbox because it kind of looks like it's appropriate to a kitchen scene. It kind of looks like a loaf of bread, but it's obviously not appropriate. So there's some interference that's going on here. So the takeaway here is that in the realm of vision, we can use our knowledge of what is contained in scenes, what objects or items are normally contained in scenes, to help us perceive our world, to help us disambiguate ambiguous visual images. So we've come to the lecture review. Question 1. What's the inverse projection problem? Question 1. What's the inverse projection problem? So the inverse projection problem is simply this idea that perception starts with a retinal image, and that image is ambiguous. We do not know what object in our world created that image, and we have to sort of figure that out. In next class, we'll talk a bit more about how we do that. There's actually a mathematical framework for how we might do that. Question 2, what makes speech perception so challenging? Put another way, why is the Amazon Alexa that you have in your apartment or house so terrible? What are the 2 problems that our brains face when they're trying to understand speech? So question 2, why is speech perception so challenging? So the first is a segmentation problem. Words slur together, and it's hard for computer speech recognition systems to sort of know where words start and where words stop. Our brains somehow do this quite easily. The second problem is that there's a lot of variability between speakers and speaking contexts. So you can speak to people who have accents, or their speech is at a different pitch than yours, but you can still somehow understand them. Very challenging problem for computer speech recognition systems to solve. Third question, sort of a general question, how does top-down information help us perceive our world? And maybe I'll just reframe this to just say, first of all, identify what is top-down information, where does it come from, and how do we use this to help us perceive our world? So question 3, how does top-down information help us perceive our world? We draw on learning, memory, and contextual information to help us disambiguate visual and auditory signals. And I think that's the key idea there, right? Top-down information reflects learning, memory, and contextual information, and we're using this information to disambiguate these bottom-up signals that are sort of necessarily ambiguous.